All right. What's wrong here? Let me unmute everybody.
It looks like it is recording.
Yeah. Okay, let me unmute everybody. I just want to record also your talk, not just mine. How about Kristen? Okay. Okay, I think it's fine. All right, let's start. So let me just share my slides. So, so can you guys see the PowerPoint presentation?
Yes.
Yes.
Okay, that's good. So for today's session, it's kind of an introduction session to the whole course, and basically we're gonna cover the essential question: what this class is about, and also I would like to. I just did the self-introduction to you guys, and also I would like to kind of hear from you guys, and you're gonna do some introduction to me and your classmates, kind of others, and get to know you, and also I can hear from you about your opinion to the class content, because probably you guys have checked the syllabus on iLearn. I'm not sure whether you checked or not, but basically what I put there is kind of the temporary content. We can do some adjustment based on your input, because it's not a undergraduate course, and also it's advanced topics. So I would like to shape the class to fit the need of graduate students. Especially you guys have, most of you have the experience in the manufacturing, in a lot of experience in this area. So it's better to kind of, all of us, we input to the content of the class to kind of shape it to satisfy your needs. All right, so as I mentioned, basically, I will introduce the logistics, the activities, the policies of this course, and also, more importantly, we need to get to know the objectives of the goals of this class, and also we could have some discussion on some of the content of the class. So as I mentioned, I'm an assistant professor in mechanical engineering department at Tennessee Tech, and you could reach me through this email. Let me just use the laser pen. All right. So through this email, as well as you can access my homepage and to get to know some of my research work. So before I joined Tennessee Tech, I'm a postdoc research fellow at Purdue University for about 3 years, actually more than 3 years. And but before that, I was a PhD student at the Chinese University of Hong Kong in Hong Kong. And you can see the two campuses of the two places I stayed. The left one is Purdue, and the right one is Hong Kong. I would say it's quite different from each other. One is kind of a typical Midwest view, and the right one is kind of island sea view. It's quite interesting experience for me. All right, so this is some brief introduction on my background and on my experience. So now you can see some of my previous research or ongoing research work. Can you see that? This page?
Yes.
Okay.
Yes.
So my research focuses on the design for additive manufacturing and some new emerging process of additive manufacturing. So as you can see, this one, the leftmost on the top, is kind of some customized wearable stuff for human. Basically, this is a customized helmet, which can be additive manufactured, right? And the middle one is a conformal cooling channel. So for the injection molding, the cooling channel is quite essential to kind of generate the high quality products and improve the production rate. But how to make the cooling process as quick as possible, as well as to make the cooling process have better heat distribution, right? So if the heat is distributed unevenly, eventually the product will have some distortion, right? So how to make this process better performance? Then one of research is generate this kind of conformal cooling channels such that it can be used for the those injection molding process. This channel can be through additive manufacture using those selective laser sintering or melting approach. And another one is a biomedical application like this one. So this is called a surgery jig. So this jig can be installed on the bone, and anything in between of these two sides will be cut. So let's say there's some tumor in between here maybe. And this jig will tell the surgeon where to cut. So it's very important for planning a surgery. But the thing is how to automatically generate them, which will make this structure stably installed on the bone, right? So that is another my previous research. For this two is kind of some ongoing project. One will be the augmented reality-based smart manufacturing systems. So how to allow the people to access those smart manufacturing systems more easily, more intuitively. So basically, up the idea using the augmented reality glasses, right? Here shows some examples. So people can wear the glasses and design something onto some physical object. And these designed virtual objects can be physically realized using the smart manufacturing systems. So the user will have a very good experience because what the virtually built can be immediately physical generated using the manufacturing system. So the last one will be a multi-directional additive manufacturing process. So as you can see, in this process, the more degree freedoms are introduced into this additive manufacturing system, because the previous additive manufacturing systems, they're all unidirectional. That means there's only one direction, and all the layers will be accumulated in one direction, layer by layer. So the question is, what if we have more degree freedoms, like the picture shows? We have more rotation degree freedoms, such that we could divide the whole part into different sections. And for each of a section, we could have a different printing direction, such that maybe there will be no support required. Also, with more degree freedom introduced, we could embed all the functional components during the printing process, such that the final result will be something with the full function over here. So that's the idea of the multi-directional additive manufacturing. And this is a new area to explore. So I think you have some ideas on what I have done and what I'm doing in the past, right now. And so now that's your turn. So I would like to ask you to introduce yourself a little bit. In terms of your name, the department, or your position, and what is your study level. I assume there's no undergraduate students, right? Only master and PhD students. And also introduce a little bit about your background, right? And your research interest. And more importantly, how your research related to additive manufacturing. and why you take this course, what's your expectation to learn from the course, and anything else you want people know about you. All right. So let me see how we can do this. Maybe I just stop the sharing. Oh, okay. So who go first? Anyone?
I'll go.
Oh, okay. Okay.
See Preston on my screen. Preston, you go first.
Okay. Sure.
Okay.
My name is Preston Cloud. I'm been working in the Department of Energy for 15 years now. Almost maybe 17. I don't know. I lose count after a while. I'm currently in this program to get a master's, and the additive manufacturing class seems like something different, and like to get a little bit more information on it. I don't have a very big background in additive manufacturing, but it's new and exciting, so I'm on board.
So you are working in the energy area, right? So am I right?
Oh, so I've spent basically 17 years as a machine designer.
Okay. Machine design. Okay.
Yeah, so I typically do machine design.
I see. Okay. All right. Anything else?
Nope, that's all for me.
Okay. Who's next?
This is Kevin Shea. I'll go next if you put your bullets up there that you want me to talk about again, please.
So you want me to what do you mean?
You had what you wanted us to discuss. If you could throw that up there so we can see it again.
Oh, okay. Oh, I understand. Okay, let me share the screen again. Okay, maybe I just share the screen again. That's better. All right.
Also, will the slides be available? Are they on iLearn?
Yes, of course. I will put everything on iLearn.
Okay, great.
Yeah.
All right, so my name's Kevin Shea. I work at the Y12 National Security Complex. You may or may not know, but you have students from both ORNL and Y12. It's two separate facilities in this class.
Okay.
I'm in what's called the Specialty Mechanical Group. We do design work for all the facilities at the site, various manufacturing equipment and things like that, support equipment. I'm in the subgroup of 2 people right now, soon to be 3, that focuses on additive manufacturing design. Okay. We're doing tooling design and machine component design using additive, and then looking at other additive stuff coming down the road. And so I'm in the master's/PhD program, the direct program. My background, I started in Y12, and before that I went to UNC Charlotte, got my undergrad there, mechanical engineering. I went to Y12 straight from there in 2001. I started in inspection, so I was doing metrology equipment, supporting that equipment, keeping it running and calibrated, and then procuring new stuff. Dealt with a lot of CMMs, the PMMCs, the lights machines, and then some optical machines as well. And then I got into tooling design in 2006, and so been doing tooling and machine design ever since. And then in about 2012, I did our first additive tool. And so since about 2015, I've been pretty heavy in additive.
I see.
My areas of interest are obviously, something additive related. Yep. I do like robotics a lot too, so hopefully I'll be able to mix something in there.
Okay.
Taking this, and then, no, go ahead.
Okay, sounds good. Okay. Who go next?
My name is Robert Cole. I'm a shift technical advisor at Y12. So I'm in one of the storage facilities here. I'm have an undergraduate degree in civil engineering. I'm in the direct master's PhD program. As far as background, I've got a total of about 10 years experience, all nuclear. 6 of it's in commercial nuclear, 2.5 or so is in construction, and 2 of it's out here on the DOE side of things. as far as taking the course, I'm interested in additive manufacturing. It looks like it's the kind of the future of where things are going. I'd like to get some background knowledge and involvement in where that heads, both personally and as far as the site's concerned.
Okay, sounds good. Next.
I'll go next.
Okay.
My name is Clay Jordan. Currently work at Oak Ridge National Lab and Dynamic Systems Analysis Group. Have an undergraduate bachelor's in mechanical engineering from University of Tennessee in Knoxville. And I'm in the master's PhD program at Tennessee Tech. Worked in, since graduating, spent about 1.5 years working in kind of a manufacturing and assembly environment commercially, and then got into the United States Centrifuge program for about 9 years in rotor balance stand operation and general testing. Then moved to Y12 for about 2 years, back in manufacturing, and have been at Oak Ridge National Lab since October of last year. Vibrations and dynamics are my primary interests, but have a lot of interest in this. Basically, this course is something new and different, and very curious to get a better footing, learn some of the strengths and weaknesses of additively manufactured processes and products. Yes, that's kind of the short of it.
Okay, that's fine.
Sorry, I guess I did mention I don't really have any experience in additive manufacturing.
Okay.
That was one.
Got it.
So I'm no Kevin Shea.
Okay.
We're all experts. My name is Tommy Hazelwood. I'm also in the Dynamic Systems Analysis Group at Oak Ridge National Lab. Worked here about 3 years. Do data acquisition, vibration, and modal analysis, rotor dynamics and dynamics. Graduated from Tennessee Tech a few years back. I'm in the master's PhD program. This course, I also know nothing about additive manufacturing, so I'd like kind of a broad informational standpoint of what we could potentially use this for and when and where to use it. That's probably about it.
I see. Good.
I think we're missing Scott Vanderland, and he may not have.
Oh, okay. My name is Scott Vanderland, and I'm a mechanical engineer at Oak Ridge National Lab. And I'm also in the PhD program. My background is I went to Tennessee Tech, graduated in 2004, and then I worked at Arnold Engineering Development Center for a couple of years, testing jet engines. And then I worked at Y12, did some manufacturing and quality control type stuff there. And then again with the American Centrifuge project, did manufacturing and quality control. And then started here at the lab 2.5 years ago.
Okay. Sounds good.
If there's no one else, Doug Clark is here too with me.
All right. So I'm Doug Clark. I'm the Chief Facility Safety Engineer at Y12. I'm in the PhD program. This is my 3rd attempt at a PhD. I've been taking graduate classes for 20 years. My research interests are in heavy metal aerosolization and manufacturing techniques. We generally spend between $5 and $20 million a year on various additive technologies. What do I want to? Why am I taking this course? It's offered, and what do I want to learn from the course? Well, we're deploying so many different technologies rapidly. It's hard to keep track of what all's going on. So.
Okay. So you are sitting with Kevin, right?
Yes.
Oh, okay, that's why I'm confused because it's showing me Kevin's talking. So what's your name again?
My name's Doug Clark. Kevin's logged in from a conference room at Y12.
Oh, I see. Good. Clark, right? Am I right?
Yes.
Okay, thank you. I'm trying to memorize all the names, all your names. I'm really bad at names. So who else? Anyone else want to talk? No? All right. I think we have all the students who are participating in this session talk about their, introduce themselves a little bit. So I think you guys have a lot of experience, especially those hands-on experience in the manufacturing and also other mechanical related areas. I think that will be a good point for me to progress this class. And also, probably based on your background, I need to adjust the content a little bit. And especially previously, I set up a project session and to improve the students' hands-on experience. But I'm not sure whether that is that necessary for you guys. And we will talk about this aspect later when I talk about the grading, the assessment of this class. Okay, let's continue. All right, so as you might know, basically our lecture will be 2 sessions, Tuesday and Thursday, 2 to 4 p.m. Eastern time. So that is Eastern time. And the Tuesday session will be at the O&L facility. And for the specific room, I haven't have the room yet. I will figure out and let you guys know as soon as possible. And for the Thursday session, there will be a Zoom session, just like what we have today. And also, I put the link of the Zoom session here, just in case you don't know what is the link. All right, and so next.
I have the Tuesday room set up for us. We've used it in the past, so the students know where it is, but I will come find you and bring you to it.
Okay, thank you so much. I will update this information as long as you send me the information. All right. So the websites, I heard from some of you that you never use this. You rarely use this iLearn. I recommend you to check it because I will update all the materials and also some announcements to this iLearn. Of course, I will also email you for those most important information, like for the time change of today, time and the location change of today's class. I emailed you through the O&L email. But for the most of the information and the materials, I will put it onto this iLearn webpage. So probably you need your student ID and password to access your classes. And if you have chosen this class, you will have something when you open this iLearn webpage. All right? And I recommend you to check it frequently, especially before the class. And you will find some material I posted. And that will kind of make sure you have all the latest updates. All right, if you have any, yeah, go ahead.
To be 100% sure on this, the course number is 6900, correct? Because the slide one you had showed as 6990.
Yeah. Because this is a special topic. Actually,
yes.
Tennessee Tech put all the special mechanical engineering put all the special topics to be 6,900. But you have to check this the content. And
yes.
Yeah, if
your slide one of this presentation said 6990, so I just wanted
to... really? Oh, I'm sorry, I made a typo. I will correct it and update it. Sorry about that. So, thanks for pointing this out. Okay. So that is the web page. For the textbook, actually, you don't have to borrow or purchase those textbooks, you can just use my lecture notes. And I have integrated a lot of content from this textbook, and these lecture notes are self-content. So you don't really have to use this book. But if you want to check some details, you could use this book from Gibson, Rosen, and Stacker. This is a very good book, and I use a lot of content from this book. It's optional. It's up to you. If you want to check, you can find the book. All right, and also some other related books like this Rapid Manufacturing, an Industrial Revolution for the Digital Age. And another one will be the Advanced Manufacturing Technology for Medical Applications. This one is more specific for the biomedical applications. I would say additive manufacturing is quite suitable for those biomedical applications. I will introduce more details regarding this. All right. And another one is this roadmap, NSF roadmap for additive manufacturing. This one is also very good. Basically, it points out some future directions in terms of the manufacturing process and also the design methods. And if you have interest, you can check it, especially if your research is related to additive manufacturing. It's good to check this report, and you will have some understanding for the future. Actually, some of these points they made in the report have been becoming true, because this report is developed in 2009, and right now, almost 10 years, 9 years later, some of their points have been addressed. And so it's very interesting to see what they pointed out and what is the reality right now. All right? So these are some books. Any questions regarding this?
So
yeah.
Are these the books that we need to go ahead and purchase?
No. As I mentioned, okay. No, it's not a must requirement. It's kind of a supplementary. So if you want to learn more, you could go and find these books. But if you just check the lecture notes, it's good enough for you to understand. I put all the necessary content from these books. I read them and extract some useful information. I mean those essential points, and put it to this lecture notes. And also for some of the material I used from other book, I put the links. And also some videos, I also put the link there. So you pretty much you will find you pretty much have everything in the lecture notes. So yeah, as I mentioned, if you want, you can find the book.
It appears, at least in the case of the first book, the Additive Manufacturing Technologies, that we can get an electronic copy of it from the Tennessee Tech Library.
Yeah. Yes. Correct. Yeah. If you want to check it, yeah, I think this is available. Yeah.
I haven't checked the others yet, but
yep.
Anyway, before we go out and buy something.
Okay, that's good. Yep.
Dr. Zhang, are these textbooks listed on the syllabus? It affects us as far as reimbursement goes, if they are or not.
I think because they are not required. I'm not sure whether if you purchase them, you can get reimbursement or not. If you need, I can ask the department, see what they say. Yeah, let me ask them whether you can get reimbursed or not. All right.
History here has shown that if they're just listed on there, they don't have to be written as required textbooks. If they're just listed on text.
Right. It's optional. It's optional.
Thanks.
Mm-hmm. Any other questions? All right. Okay, that's good. So basically for this here shows a cone of learnings. Basically, if you check the details of this cone, you will realize when you learn something after 2 weeks, the most of the stuff you only read will pretty much forgotten, will be pretty much forgotten. But if you learn through not just reading the lecture notes or books, but through some discussion or some project, you will memorize most of them. So that this nature of learning gave us some idea that we need not only just read the lecture notes, just read the book, but also we need to have some activities, not just like some project, right? To kind of make us better understand the course content and memorize the most of the points, right? That's the idea for me to develop this class. And so the objective of this class will be, you need to understand the basic principles and importance of additive manufacturing technology, and have some idea to innovate some new process, at least know some directions. What should be the new the direction for the new process, right? And compare the different types of additive manufacturing technologies, because we have, I mean, a couple of additive manufacturing technologies. You have to have some idea where, when, and what kind of additive manufacturing technology should be used in what kind of scenario, right? So based on this understanding, you could choose the right process for different applications. And the last point of the objective will be to have some scientific understanding of the underneath physics of additive manufacturing process, right? So that is also in the cutting edge of the research, right? So the understanding of the physics process of the additive manufacturing is the current kind of a research spotlight. All right. Besides this, it's good to develop some hands-on and problem-solving capabilities. And of course, the teamwork will be another very important characteristic to have. And also, you guys, another point is to have some fun from learning, because this class is kind of not just reading textbook, not just repeating the knowledge from those old textbooks. It's kind of you need to discover something new, because additive manufacturing is relatively new to compared to other manufacturing process, and there are a lot of unsolved problems, open problems. So it's always good to discuss, to discover some new knowledge, and maybe there will be some research coming out based on this class. All right. So additive manufacturing actually is kind of an interdisciplinary topic. Different people from different backgrounds contribute to these technologies as listed over here. So that implies not just one, I mean, not just the content of one area need to be studied. It's kind of also a multidisciplinary class to learn additive manufacturing. And for the lecture, I put some content over here. So basically, there will be 10 classes, 10-week class. And for the third week, I have academic trip I have a conference to attend for the whole week. So I cannot give you a lecture. But for all other weeks, except some holiday, like the Thursday in the week 5, there's a holiday. And also, let me check. What else? I think that's the only thing we will miss, right? So yeah, except these 3 days, we will have some lectures or other activities, and here are some content we're gonna cover. All right. So right now, I would like to have one project, one application developed project, another literature review project, and some homeworks. I would like to have maybe 4 to 5 homeworks, but in total 10 points. And the participation, right? To discuss, not here, the participation does not mean you have to physically be here or something. It rather means you actively participate into the class, discuss with us, and give me some feedback, right? That gives another 10 points. But right now, I'm kind of hesitating about this application development project, because I used to give this class to the graduate. It's also a graduate level class. I gave this before, but they have very little. The students at that time, they have very little experience, hands-on experience. That's why I would like to give them some application development project. And another thing is they have 4 months to finish this class. So they have plenty of time to do this project. But in this case, as you guys, it seems you guys have some experience, hands-on experience, and we only have 2 months to finish this class. So I'm hesitating whether we still have this application development project or we have a final exam. So I would like to listen to your opinion. Anyone have some idea?
I agree. We have hands-on experience, and it's a short class.
Okay.
How about, what if we gave reviews of projects we were doing, either at the lab or Y12? It would sort of be a hybrid of the literature review, but it would be literature review with application demonstration, sort of. So.
Yeah, there's projects that Doug and I don't know, aren't very familiar with at Y12, so that would be kind of a review or a research.
Okay, so but the things we already have a literature review project is pretty much what you mentioned. It's kind of review some papers related to additive manufacturing, and you need to write a report, kind of a summary of what you reviewed, and you need to give a presentation to demonstrate what you learned from the literature review. So I think that pretty much does what you suggested. But for the application development, I used to have, let me give you some details about this. I actually have some, So this project basically is kind of, it can be initiated by either students or it can be assigned by me. Basically, it's kind of, you find some topics related to your research or interest, but it has to be an application project. That means you have to develop something, either a process or some design concept. And or I help you to come up with some ideas for the project. So what do you think?
That sounds reasonable to me.
Okay. All right. Okay. It seems you guys like the idea to have a project instead of final exams. Then I think, I mean, maybe we just keep it as it is. And if you have other concerns, you can email me separately, all right, about this project. And all right, because we only have 2 weeks, 2 months. We have to make decision as quick as possible because you have to have some time to implement the project, right?
Do you happen to have examples of past development projects that we might take a look at?
Oh,
I like the idea of a project, but
I do have some, but not on this computer. I can post it afterwards and email you some of the content, some of the samples I have for this project. All right.
Okay, that'd be great. Thank you.
Yep. Yep. All right. Okay. Let's temporarily keep this setup. All right. So for the homework, basically, is some class problems assignment. It will relate to what I talked about in the lecture, and there will be 4 to 5 in total, and it's individual homework. So you need to finish them individually. All right, that's 10 points. I would say the question will be quite fundamental. It's kind of help you to build up your foundation on additive manufacturing. So for the literature review project, it's kind of identify an area related to 3D print additive manufacturing technologies. It consists of reading 4 to 6 technical papers and write a literature survey paper and make a presentation and demonstrate your understanding. Okay. So for this literature review project and also this application development project, I'm kind of thinking, I'm not sure what's your opinion, but we could kind of
somebody's phone just went dead.
Beg your pardon? Beg your pardon? Okay. So I'm thinking about to kind of merge these two together and reduce some of the workload, because this used to be a setup for the 4 months teaching, but in case we have 2 months only, so I'm kind of thinking about to reduce the literature review project a little bit and merge it to this application development project. Do you guys agree with this, or you have some?
That does not hurt my feelings.
Okay. Any other suggestions?
It makes sense. Like if we would do the literature review before the project, that might help us pick the project topic a little bit better.
Right. Yeah.
Seems good to me.
Okay, sounds good. Because previously I separated these two, but right now I'm thinking about to merge them together. Then you will do least effort because you don't need to read that much, and you don't write 2 reports and do 2 presentations. You can just write 1 report and do 1 presentation. That will, I think that makes sense to all of you. I'm not sure. Yeah. Any other suggestions?
That sounds good to me.
Okay, sounds good. So for the participation, it's kind of, I would like to hear more feedback from you, and I would like to discuss with you, especially in the on-site session, right? We are sitting face to face, and it's better for us to kind of make more discussion on the course content, on the project, on whatever topics you want to discuss related to the class. All right, and also your feedback is valuable to me to improve this class. So I think I would like to stop here for and have a 15 minutes, 10 minutes break. And after we come back, I will start to introduce the fundamental of additive manufacturing. All right?
Okay.
Okay. Okay, talk to you 10 minutes later. All right?
I was able to just download the entire textbook as discussed earlier. It is available through the Volp library online. It just feeds you a PDF. It's about 500 pages, 8 megabytes.
All right, thanks, Robert. I'm not sure I have that much space left in my inbox.
Well, luckily you just download it. You don't have to keep it in your email. There is something available on Interlibrary alone as well. I don't know. I'm poking at this to see if it actually works. I don't know if it shows up at the library there though, or if they can send it to you.
Yeah, I don't know, Robert. We're on the leading edge of this. I mean, when I went to the conferences and the NFS thing, I mean, we were sitting there talking about when somebody dies, let's at least be on the fronting edge because we recognize the leading edge is the bleeding edge on this. We've had a lot of really interesting things, and the books, as I flip through them, are just so out of date. I mean, even the conference 6 months ago isn't up to date with what we're doing right now.
Yep, I understand entirely. Yeah, and this book's from 2010 as well, if you didn't see that earlier.
All right. Let's continue our class.
We're ready.
Good to go.
Okay, let's go. So this slide shows the definition of manufacturing. I mean, not definition, the origin of manufacturing, right? The word manufacturing actually is derived from two Latin words, manus and factus. So this combination means made by hand. So that implies the primary forms of manufacturing in the old times, right? So how about now? We have this figure shows the history of manufacturing in the human histories. So as you can see, there are two axes shown here. One is the time, and the vertical one is the complexity of the products. And actually, human began to manufacture stuff in very early age. Just look at this bison found in a cave in Spain. So basically, it was made 30,000 years ago, and they use the color and put to the stone in the cave, and which can be considered as a coating technology. And it's pretty old, 30,000 years, right? And then we go to this gorgeous bronzy statues in Roman Empire. So you can see this statue has very good details, a lot of details in the muscles and the hair. And this statue is made using the casting manufacturing process, right? But for more flexible and more durable stuff like armors, the casting does not work. You need something like those forging or metal forming. So in the mid-age, those blacksmiths, they are working on those armors for their lord or king. And until now, you will see all these manufacturing are made by hand. So how about some nature power? So in 18th century, there are some water-powered metal cutting machines, which is invented in Netherlands. And you can see from this figure, people are utilizing the natural power to speed up the manufacturing process. But even there are some new power, a greater power introduced in manufacturing, all these manufacturing has the same problems. So they are very low efficient, and the quality of the product made using these methods are usually very low quality, and the cost is pretty high. So the manufactured products are privileged for those people who have power or money, right? So how to kind of allow those ordinary people to have the chance to use those manufactured products? That's the problems. So that's why we have this industrial revolution, as you all know, right? We have the machine invented, and the water power is utilized to drive the steam machine, right? And then we have mass production, assembly lines, and electricity power utilized to further improve the production rate, and also improve the product quality. So this figure shows the Ford car, right? So because of the assembly line is introduced, we could purchase a car in a relatively low price. So that make those products from the manufacturing can be accessed by ordinary people. And in the third industrial revolution, we have computer, we have automation, right? But right now, we are in the fourth industrial revolution. We have the cyber physical systems, we put sensors everywhere, and we link all the machines using the internet or other like other communication method to
Skynet.
Pardon? Okay.
Skynet.
Yeah, kind of. Yeah, you are right, Skynet. And more importantly, we have new way to make products. That is the additive manufacturing or 3D printing. So for the first three industrial revolution, basically we are solving one problem: to make manufacturing faster, better, and cheaper. And we are successful. We were successful to achieve it. Basically, right now people can purchase those products in a relatively affordable price, right? That is all because we have the production rate highly improved. But the things we can only have the products with all the same size, appearance. So how about some personalized design and manufacturing? And how about some more complex shapes, right? So even, for example, everyone has an iPhone. I would say almost everyone has an iPhone, okay? But you can never have some personalized shape or color for your iPhone. You can only take the one Apple give you, right? But in the new age of manufacturing, that could become a reality by using the new cyber physical systems to access those manufacturing systems, such as additive manufacturing systems. People can design and manufacture their personalized products. So that's the differences between the fourth industrial revolution versus the previous three. All right? So what does future design and manufacturing look like? Let's check this figure. Actually, I quote this figure from the Economist journal. Basically, in this figure, there's a user sitting here, right? And what he's doing, he's designing his own products and using the computational design tool. And then this design will be sent to the manufacturing systems and the product will be manufactured in a personalized form. So that is the kind of the new way of manufacturing in the near future. And so I think the order of the slides has something wrong. Let me adjust this a little bit. All right. So here shows some manufactured products by those conventional manufacturing process. And here shows a new workflow for people to convert those raw material to a final products for a car design, right? For a car product. And as I mentioned, basically, due to the nature of the new manufacturing method, we have something relatively new to the previous manufacturing process. That is the capability to personalize your products. All right. I think I have another slide to show you. Sorry about that. I just use a wrong slides to show. All right, so here we go. So as all you have seen on my previous slides, so additive manufacturing gives the new capability than other conventional manufacturing process. So what's the definition of additive manufacturing, you may ask? So additive manufacturing is the official industrial standard term from all applications of the technology. It is defined as the process of joining materials to make objects from 3D model data, usually layer upon layer, as opposite to subtractive manufacturing method. So basically, this definition is given by the Euler Association, and that there are some points here. So first of all, it implies the direct digital manufacturing nature of additive manufacturing, which means it will produce the 3D object directly from the virtual 3D model. That's point one. Another point is the layer upon layer manner of additive manufacturing. So I would say these two are the most important features for additive manufacturing, at least for current additive manufacturing process. And there are some different names for additive manufacturing. The first one is what we are using, additive manufacturing. And 3D printing, I would say, is kind of a layman name for additive manufacturing, which is also very popular, especially for those novice users. And in the early age, additive manufacturing used to be called rapid prototyping, right? Because people use it mainly for typing their products. And also, even in earlier age, it is called the solid freeform fabrication. Actually, there's a very famous conference. It still uses this name, solid freeform fabrication, and so on and so forth. So all of these names, actually, they all refer to the same type of manufacturing process, which is defined here, right? So what is the features for additive manufacturing? It can produce objects with complex geometry, like the ones shown here. You can see these objects with very complex geometry, which cannot be manufactured using other manufacturing process. And it enables the customization. Here shows two successful applications for additive manufacturing. One is a customized teeth aligner. Another one is also a customized hearing aid bus. For some of these applications, additive manufacturing achieves lower cost, less material, and better performance. So like the one showing here, this fuel nozzle actually is the application used by GE. Basically, this is a fuel nozzle used on the airplane, and it is 25% lighter than the previous design and 5 times stronger than the previous one. And also this bracket is manufactured for the Airbus A320. So as you can see, compared to the original design, this new design is 30% lighter. So for those applications in the airspace or airplane, the light is very important. Lighter parts means less money consumed, right? And that is very essential for them. That's why they are very actively developing additive manufacturing applications, especially those metal process. Also, additive manufacturing turns the consumer into maker. So again, for this figure, this person can design and manufacture his own products, not waiting for the big companies to produce it for him. So that is very essential to democratize the design and manufacturing. And it also enables some new production models, right? Like this, because we have these desktop level additive manufacturing printers, we could design and make at our home, right? We don't need to wait for those big companies produce the product for us, right? And we have those online manufacturing services. We can access manufacturing systems just through apps or a web page, right? If you have some idea, you can just design the products based on your idea and send to those manufacturing systems, and these systems will produce the products for you. And there will be some people help you to complete this manufacturing process.
On the previous slide,
yeah,
looking at the A320 bracket,
yeah,
and the fuel nozzle,
yeah,
well, even the hearing aid and teeth aligner, even the hearing aid bud and the teeth aligner,
yeah,
above, I'm making the assumption that there's some kind of a post-processing done, a machining operation, maybe a heat treat for strength.
Correct. Correct.
Is that correct? And I guess where, those of you who are more knowledgeable of this than I am.
Oh, yeah.
Where would all of this, I guess, what would the overall process be? Would
yeah,
it be
exactly.
then do this, or can you actually get a near final finish using some of the higher end 3D printers?
Well, I would say, especially for these two, the teeth aligner and hearing aid bud. Basically, if actually they are using those lithography-based additive manufacturing process, and they can generate very high quality products, surface finishing, but still you need to process, like post-processing them, especially for the hearing bud. It only generates the appearance. You need to assemble the component into it, right? So there's still some manual work has to be done. So at this point, you're absolutely right. There's still distance from additive manufacturing towards the generating those end products. And that's one research direction, actually. It's, for the metal one, of course, there will be a lot of treatments after the printing. The surface finishing will never be as this. There's some post-processing definitely necessary to make the final products. Yeah.
Okay. All right.
Yep.
Thank you.
Yep. In the, I mean, actually, I will tackle these problems later on.
Okay. All right.
When I talk about the future directions, there are some research efforts which are targeting at generating the end products using additive manufacturing, assembling the components, functional components into the printing process. That's a kind of active research area right now. Okay.
Okay.
All right, so for the more broad impact of additive manufacturing, basically it has a potential to turn the manufacturing from a resource-centered to a idea-centered. So for the current manufacturing, you have to have the resource, right? You have to have the money to build up the facilities, to organize the people, to organize the supply chain for the manufacturing, right? But for the new paradigm of manufacturing, essentially the most important thing become the idea. So if you have some idea, and because of the new manufacturing system and the cyber physical systems, you could turn your idea into some physical products by just using the computational design tool and those easy to access manufacturing systems. And then your final products will be produced for you. I'm not claiming that additive manufacturing or the new way of manufacturing will take over all the conventional manufacturing method. But I'm talking about some new options, right? Before you have no options other than just mass produce the product. But right now, there could be some alternative. And well, it's hard to see whether this will totally change, it will totally take over the role of conventional way of manufacturing, or they two will exist in parallel. Well, I lean on the second kind of scenario. We have both the conventional way of manufacturing and the new way of manufacturing. But the idea is, for the new way of manufacturing, the idea becomes the most important thing. And also, it democratizes the design and the manufacturing. It provides the opportunity for ordinary people to access the design and the manufacturing. So because of the nature of the additive manufacturing and the cyber physical systems, it breaks the geographic restrictions for people to design and manufacture. So this is Henry Ford, right? The founder of Ford Motor. Basically, he used to be called the father of mass production or the assembly line. And there's a very famous story he told to the customer who want to buy a car. He said, you can purchase the car with any color you want, as long as it is black. So it's quite funny, because in his mind, and that is kind of also true even today, for mass production, it's really difficult to have some customized feature, right? It will greatly increase the cost. It's so difficult. So now the people, they are all purely consumer. They can only take what the big company provide, right? So the new way of manufacturing with the power of additive manufacturing has enabled the opportunity for the ordinary people to design and manufacture. So that's the whole point for in this end. All right. And also, as you can see, additive manufacturing has tons of applications, and you can see from those online media or newspapers, and there's something new always appear days and nights, and it involves in almost every aspect of human life. And I heard that actually I visited ONL once last year, and I had the chance to check the car printed using the giant FDM machine in the ONL. So that's quite impressive. And also for some tiny stuff like those, like the one shown here, people can even print some food which has customized shape and taste, right? And also for the biomedical applications, right? People are, I mean, researchers are looking at the chance to generate some organs using some bioprinting process. Oh, by the way, I will introduce some of the bioprinting techniques in the later slides, in the later lectures, right? So this slide shows the market segments of additive manufacturing. As you can see, not only the prototyping, but also the end product, additive manufacturing are involved. And of course, for the end product, it has higher requirements in terms of the strength of the part and also the accuracy. But the new technologies are pushing the boundaries of the capability of additive manufacturing. And some of the applications, like what I showed you in the previous slides, has changed the way people thinking about additive manufacturing. And also, the additive manufacturing market is growing day and night. And we are pretty much here, right? And based on the current trend, we can project later on, we will have more, we will have larger additive manufacturing part market. And also you can see in different areas, they all have the needs for the parts generated by additive manufacturing, including the aerospace. I would say that is a very big market, and also some biomedical, right? Automotive, electronics, and consumers, right? Also, researchers have developed all different additive manufacturing technologies. And we can tell from these figures contains the patents on additive manufacturing in recent decades, right? You can see the trend of this patent application is growing every year. Actually, there are people, I mean, there are some well-known manufacturers for additive manufacturing systems. And in the consumer level, especially the FDM machine, we have the MakeBot, Ultimaker, and also ZCOP, 3D system, and so on and so forth. They are mainly for those consumer level applications. And also you could find some industry level applications like this EOS, which is the main player for the metal printing, right? They are provide the metal additive manufacturing systems. You can see it has fairly big shares in the market of the manufacturing systems. And the major medias are covering the additive manufacturing. As you can see, the one I quote from the economist, and also the Forbes, CNC, and so on and so forth, Times, and the New York Times. So you can see all these medias are looking at the development of additive manufacturing, and they are willing to let people know what happened there in the area of additive manufacturing. That means people are interested in these areas And this is also verified because based on the fundings agencies. So they are funding the project on additive manufacturing in quite a lot in recent years. And some industry giants, they are also working in the additive manufacturing areas like GE, like Boeing, Ford, and Nike. So I would like to show you some of the videos, but let me try to share the video to you. Okay, let me. Can you see the web browser? Nope.
No, we still just see the slides. You might need to exit the presentation.
There you go.
Yeah, there you go.
Can you see the audio? Can you?
Audio is pretty quiet.
Pretty quiet. Okay, let me do that. All right. Okay.
My wife likes to say nothing around our house breaks permanently. I think there's something just in my personality that draws me to solve problems like that. My name is Josh Mook, and I'm an engineering leader at GE Additive. Additive manufacturing is essentially 3D printing, where you're taking a design file in a computer, slicing it into layers, and melting the individual powder particles layer by layer. We can now produce geometries that before could only be drawn. As an engineer, what motivates me is really designing things that no one has ever imagined before. In the beginning, I started at GE Aviation. My love of flying is really what drove me into the field of aerospace. My grandfather was a pilot. He was the one that introduced me to flying at the age of 2. My time as a pilot really made me respect the technology. Jet engines are like a symphony of very complex components working together with just human hairs with the clearance between them. At GE Aviation, I was fascinated with big problems in engines. When GE decided to develop our own fuel nozzle, it's something that almost consumed me. There's a lot of science. It almost sometimes feels like magic inside designing the perfect combustion system. You would have seen sketches from me everywhere. I would say at least once a day, we felt like there is no solution. I realized that the only way we were going to ever meet is to use a manufacturing technique that we had never used before. Additive is perfect for this part, really because of the complexity level. You have a very small component where you're trying to fit this amazing amount inside of it, that I can print it as a single piece, which is more efficient, lighter, and more durable. My wife often calls the fuel nozzle our 4th child. And it felt like that. After the fuel nozzle, in the jet engine, we replaced over 855 components, just 12, using this design technology. Ever since then, we realized that additive can be so much bigger. It is going to revolutionize the way all products look and the way they're manufactured. We're working in medical, oil and gas, power generation, automotive. Really, every industry is ripe for design disruption. It's completely shifting how the engineer approaches problems. And that's the most exciting part about my job every day. I believe my kids and this next generation are going to grow up with possibilities that we couldn't imagine.
All right. So basically, this shows the story for the fuel nozzle produced by GE. No, this one. So can you see the presentation?
Yes.
Okay. So I don't know whether you noticed you noticed that or not. Basically, the guy in the video mentioned they managed to reduce the components in the number 800 to only 12, right? So that is very essential for the applications of airspace and airplanes, right? And that is a very, I would say, a major benefit for additive manufacturing in the industrial applications. If you have taken the design for manufacturability class, you will know the number of parts or components will greatly impact the cost and the reliability of the machine systems, right? So if you can find a way to reduce the number of the components necessary and needed, that's a lot. I mean, that's essential, right? So I will introduce more in more details about this aspect. Okay, due to the time, I won't show all the videos, but there's another one from Nike I would like to show you. All right, let me. Let me find where it is. Oh, here. Can you see the screen, my screen?
Yes.
Okay, good.
Last year, Nike got ahead of the rest of the footwear world as the first company to release a shoe with 3D printing. The production of the Vapor Laser Talon did not simply use 3D printing for the but incorporated a 3D printed plate product. This year, the company is making headlines again with their updated football cleat, the Vapor Talon, which will make its debut at Super Bowl 38. With the Vapor Laser Talon, the design team at Nike worked with Olympic sprinter Michael Johnson and his MJP NFL training center to design a shoe optimized for use in the straight line with quarterback dash. The Laser Talon successor, also made with the help of is meant to expand the shoe's design and used by an entire football team. The Carbon Elite, therefore, was needed to increase the speed and traction for linebackers, running backs, and quarterbacks, regardless of the direction. Like the Laser Talon, the design of the Carbon Elite was focused on the zero step of the player, movement at which the player begins. The goal was to reduce the slippage that may occur during the zero step as much as possible. The head of innovation at Nike, Shane Kapatsu, explained how the entire design process was sped up dramatically. Something like this would have normally taken Nike 2 or 3 years at least. They accomplished this in 6 months. Let's see how Nike accomplished this new design in this video.
Above all else, push the what we got out of that was not only making it faster, but actually telling us forward in the future. Michael Johnson told us, let's focus. Let's get that ignition off the line and make sure we have zero step identify certain techniques that best use to get out of the box. The Vapor Laser Talon product saying to you, how do you translate complete workout data, basically a track into performance racing built vapor carbon better silver represents ultimately highest honor.
All right. I noticed that some of you cannot hear the audio well, so let me give you a little explanation of this application. Let me go back.
We are here in Baltimore. Under Armour's part.
Let me share my. So basically, the idea is to improve the athlete's performance by designing some new structures of the insole of the shoes, not the whole shoes. They still need to assemble the upper part of the shoes to the bottom part. What they customized and redesigned is the bottom part, the insole. They did some study with the athletes Michael Johnson, and they figured out that the zero step, that means when the athlete is about to departure, will greatly affect their performance, and they are trying to make sure the feet of the athlete won't be slippery when they wear the shoes. So that gives them ideas how they're gonna design the geometry of the insole. But as the geometry is very complex, so there's no way to produce them using the existing conventional manufacturing process. That's why they use additive manufacturing. Actually, they use the powder bed-based additive manufacturing process. So that's the background story of this video. All right. So basically, what we just watched are the two applications. One for the industry level applications. Another is kind of a consumer level. Although right now it's only for the professionals, but I believe sooner or later it will become some consumer level applications products, right? And hopefully it gives you some ideas of the applications of additive manufacturing.
Yeah, because sorry,
yeah.
I thought that it was either Z Corp or Stratasys, or maybe even Object, that was looking at the flexible AM stuff to actually fabricate outsoles for Nike a couple years ago, and then actually made an entire what looks like a croc.
Mm-hmm. Okay. Yeah. I think those companies. Yep. What was that? Okay.
No. Yeah.
I think that was feedback.
Yeah.
Okay. Yeah. Yes. So I think those companies they are actively looking forward some new designs. They already have the new designs. They already have the ideas. The only thing is they cannot implement them. There's no way to manufacture their new crazy designs in the old time. But right now there is additive manufacturing. They're powder based, they're polymer based, stereolithography based. They could actually physically make their design to a product. So that's the whole point for current applications. And as mentioned in the fuel nozzle case, basically they came up some optimized design, right? But it turns out they figure out there's no way to manufacture them using current manufacturing. Those conventional manufacturing process. So they have to use those metal printing, and the new additive manufacturing process enables the chance to realize some optimized and new designs. So that's the whole point for additive manufacturing in both industry and consumer level. All right. So and this for the hardwares of additive manufacturing, you can see some very well-known brands, right? And here list 10 famous additive manufacturing system manufacturers and suppliers. So like the 3D Systems, Stratasys, HP. HP is new to additive manufacturing, but they grow really rapidly. And their additive manufacturing systems, actually they took over those high-end consumer level market a lot. And also some new concept of metal printing, like desktop metal and Markforged, right? That concept is they developed the systems which is much cheaper than the laser-based. I mean, than the powder, the previous selective laser sintering or melting-based ones. And so some examples shown here, the desktop metal one, and the older one is this US machine, right? So the cost for the machine and the materials and maintenance will be greatly reduced if this kind of desktop level metal printing become better and better. All right, and also the carbon company is carbon. It used to have the name Carbon 3D. Basically, this company, they have a unique technology which allows a continuous motion of the additive manufacturing process. That is very efficient compared to the conventional ways. And based on their data, they claim they achieved 100 times speed up compared to the previous additive manufacturing process. And also they focus on the biomedical and consumer level applications. So here are some, these are some those manufacturers. And also automaker. I would say automaker is a very good consumer level additive manufacturing systems. It costs $3,000-5,000 per system, but it works pretty good. And actually, in my lab there are two, and in my colleagues' lab there are several. So it's quite reliable and it's cheap. I would say it will grow even larger in the consumer level market. All right. In the software side, you can see there are a lot of new software support additive manufacturing, design for additive manufacturing. And not only those big companies like Autodesk, right, like this one, but also some new startup companies like those Onshape. Although it's ranked only 20, but actually I would say it's quite interesting software. The point is this Onshape, they provide a cloud-based environment, allow the user to design on the cloud. So you don't need to install the software onto your own computer. You just have the internet access and also visit their webpage. Then you can do the design purely on the cloud. So I would say that represents the future direction of the CAD softwares. So, all right. So actually, there are 10 principles for additive manufacturing. Some of these principles I've already talked a little bit, and let's check them in more details. Oh, by the way, basically the 10 principles actually they come from this this book, and I think they did a very good summary of the principles of additive manufacturing. So the first principle of additive manufacturing is the complexity is free, which means you can produce products with really complex geometry using additive manufacturing without additional cost or setup. As you can see, these applications generated using additive manufacturing, they are really complex. And I mean, some of them, I would say, is really difficult to be manufactured using those conventional manufacturing process. But for additive manufacturing, there's no big differences to produce these versus those products with simple geometry. So that is the principle one, complex is free. So the principle two is variety is free. So one 3D printer, one additive manufacturing process can generate all different products with all different geometries, like the one shown in this figure. Actually, they are all manufactured using one single additive manufacturing systems, probably the fuse deposition systems. So that is very different from the conventional machine systems. For the conventional machine systems, to generate one specific product, you have to set up and to have a specific machine tool put there. And if you change the machine tool to generate another type of product, you have to do the setup again and do the calibration, everything again. So that is very different for additive manufacturing. Basically, what you need to do is you just pass the different model to additive manufacturing systems, and then click on the start. That's it. So there's no actual effort need to be done for you to produce one product from another one. And using additive manufacturing, the assembly could be improved. For example, this chain actually is movable, but it does not require any assembly. So how to achieve this? Basically, this is achieved by setting up the proper tolerance and use the solutable support materials. So after printing out from the additive manufacturing systems, those support materials can be removed, or you just put it into the solution, and then the support materials will be gone. And then you will have this chain with the motion achieved without any assembly. Also, some case like this, the elephant, this animal case, basically the ball joints, the motion joints can be designed to the model. So if you just carefully set up the tolerance and choose those solutable support material, those rotational motion, those ball joints can be achieved without any assembly. And again, we are checking this GE fuel nozzle case. So it used to have 25 assemblies for the old design, for the old products. But after combining the component together, right now there are only 5 different components for this nozzle. Right? And for this case, the old design has 16 parts, and to assemble them, you need to use screws and glues, right? But how about we modify the design to this one and use additive manufacturing to manufacture it. So there's only one part, and there's no assembly. So the total assembly free can be achieved for some of these applications using additive manufacturing, which is essential for the applications for design for the manufacturing and the assemblies. So for the principle 4, 5, 6, and 7, we have 0 lead time, 5 unlimited design space, and 0 scale manufacturing. Compact portable manufacturing. And they all kind of related to this, illustration figure. Basically, all these principles are related to the accessible and easy to use features of additive manufacturing. So we can access the additive manufacturing systems using these desktop level machines, consumer level machines, or through those online services. So people can easily access the manufacturing facilities through these forms based on additive manufacturing. I may stop here. And for the next class on Thursday, is still a Zoom session. And so any questions or suggestions to today's class? Anything? Okay. Okay, good, good. So for the course project, I will update because I'm gonna kind of merge the literature review class project with the application project. I'm gonna merge them together and give you a guideline and post it on iLearn. Also, I will try to post some sample projects in the previous class. All right, that will help you to understand what's the expectation for the project. All right.
Sounds good.
Okay.
Dr. Zhang, did you say if you were going to the next before the class so that we could print them?
I didn't hear clearly. Can you see again?
Would you? This is Kevin. Would you be able to post the next class's slides at least before the class so that we could print them and have them to make notes on it?
Yeah. I will do that. I will post today's lecture notes and the next class next notes before probably today or tomorrow sometimes before the class.
Okay, yeah, as long as it's like around a day before, you know, because I can't get them right away and then print them and have them here.
I will do that. Okay.
Great, thank you.
Thank you guys.